Hello everyone. Uh, During the lecture today, I want to jump ahead to chapter 9 that will be relevant for lab 3. So we'll come back to some of the earlier chapters later on, but what I'm specifically interested in is, at least initially, is subroutines. Okay. Some of you may already be familiar with the idea of subroutines. If you only have programmed in MATLAB in the past, you may think of a subroutine as a function, basically the same thing. Okay, but let's, before talking specifically about subroutines, let's talk about the alternatives. Okay, so we often find that there's segments of code that are required repeatedly. Okay, so we may have some aspect of our program that we want to do over and over again. Maybe we want to continually or frequently write out to the LEDs on an output port, or read from the keyboard regularly to check for keyboard inputs. Okay, so this segment of code, if we call it a routine, it may only be a few lines of code. Okay, and as such, seems like it might be simple enough to just copy and paste that code each time you need it. Okay, but there are downsides to that approach. If you determine that you need to modify, or maybe you had an error in that small segment of code, any modifications that need to be done would have to be done to each and every copy of that segment of code. Okay, so that can be both time consuming and can lead to errors if you happen to miss updating one of the copies. The other aspect to this approach is that each time you create a copy of that code, it requires extra lines of code in your program, and as such it's going to require extra program memory as well. So it's going to take up more memory in your computer to store these multiple lines of code. Okay, so let's look at a example of this approach, just something pulled from the course notes. So here's 3 simple lines of code that are used to read a port that has switches connected to it somewhere else. We've defined the address of the switches, so we read those switches in, and we're maybe only interested in the least significant 4 bits of that port, or the least significant 4 switches. Okay, so we said needed that code maybe 3 times, maybe more than that, and we've just duplicated the same code multiple times in our program. Okay, but as I said, if I decide, oh, maybe I want to mask off and read from the bottom 5 switches. Well, I changed it in this program. Well, I have to make sure I go and change it in every copy, and I said there could be many copies, I could miss a copy, and now all of a sudden sometimes I'm not checking that 5th switch, sometimes I am. Leads to problems and challenges in debugging the software. Okay, now let's talk about the value of doing this through the use of a subroutine. Okay, so a subroutine is a segment of code that's designed and debugged separately from the main program. Okay, so in a sense, that code can kind of stand on its own, and might be used independently of the current main program, because if designed well, you could use it for other programs, like the read switches idea. It's likely that we will need the ability to read switches for different applications, not just the current one you might be working on. So you can be strategic when you design your subroutine to try to make it as universal as possible. In contrast to the example above, it's stored only once in memory, and stored separately from the main program. And usually it's placed just immediately after in memory. Now, again, any of you that are familiar with subroutines are aware that we can have subroutines that actually exist in other files that we include as well. So they don't even necessarily have to be in the same text file that could exist in another text file that we include with this. But in assembly, for simplicity, it often is the subroutines will just fall immediately after your main program. The subroutine is run on demand as needed. From within the main program. Okay, and this is done through the use of call instructions. Okay, the call instruction is used to branch to a subroutine. Say a subroutine. And it does this through an address label. We will give our subroutine in a label, an address label, and then we'll use that address label in the call instruction to redirect our program counter to the position of the subroutine. So replicating kind of the application above, where we had 3 instances in the program where we needed to read the switches, that might be done with a call instruction, a call to a subroutine. And now instead of you having 3 copies of the the instructions associated with reading the switches, now we just have 3 call instructions that redirect our flow of code to go to the subroutine wherever it may be located, as specified by the address label, and execute that code. Okay. When we're done with within the call within the subroutine, we have to have a means of returning back to our main program, right? So we call the read switch that goes to the address given by the address label, executes those instructions, but then we want to come back and execute these lines that are back in our main program. That is done through a return instruction. So a return instruction is used to branch back to the statement immediately following the call instruction. Okay, and as such, that return instruction is going to need to be the last instruction you do in the subroutine, because that's going to return you back to the main program. Final instruction of subroutine. Let's look at an example of what a subroutine might look like for, again, using the same example of reading the switches. Okay, so here is the read switch subroutine that's being called in the example up above here, and we see that we have an address label that gives this subroutine a name and really keeps track of the address of the subroutine, but otherwise the subroutine looks identical to the program, the lines of code that we looked at initially, which is what we wanted to perform, was reading the input port that the switches are connected to and masking the least significant 4 bits. So we see this is doing that same job. Now if I decided, I wanted to actually check the all 5 switches up to SW0, 1, 2, 3, and 4. Now I could change my mask. I only need to change it once, because the same subroutine, the same chunk of code is called every time I want to do the read switches through these call instructions. Note that the last thing that we do is a return. Let's talk a little bit more about what exactly happens when we perform the call instruction. Okay, the call instruction does a couple things. First, it saves a copy of the program counter to the register called RA, where RA stands for return address. Okay, and then once that program counter is stored in the return address register, the program counter is updated with the address of the subroutine of interest, the subroutine that's being called, and that is done via the address label that is referred to in the call instruction and is used to label the subroutine like we see here. So using that address label will take the address associated with that address label through the call instruction and put that address in the program counter. Okay, so this is this second step of updating the program counter with the address of the address label of the subroutine is basically a branch. Okay, so it's just a branch, like a branch to the subroutine. So we've looked at branch instructions already, we've used them. The difference is the call instruction has this extra step where it saves a copy of the program counter to the return address register. Okay, so what's the value of having the program counter in the return address register? Well, if it wasn't already obvious, it's for when we use the return instruction, because the return instruction simply takes and copies the return address register back to the program counter. Okay, now remember that when this call instruction, let's go up here and think about this. So let's say that there's an instruction immediately after here. I don't know what it is or something. This instruction is going to be at the next address in memory. When the call instruction is executed, the program counter is put in the return address instruction. Remember the steps of our fetch and execute cycle. We fetch this instruction first, right? This gets fetched. Program counter gets incremented. Let me use lowercase to be consistent. Right, so in this case, the program counter would be equal to 100. I'll put the whole address here for clarity. Okay, and then the call instruction is executed. Okay, so when the call instruction is executed, the program counter is already pointing at the next instruction that needs to be executed. So having the return instruction take this address and put it back in the program counter is exactly what we want. That'll cause the program counter to pick up from the where it left off at the instruction immediately following the call. Okay, let's so we'll note that this subroutine that we used in the example used some registers, right? We have register 5 being used, register 3 being used, and actually a value being returned through register 3, right? This register 3 is going to hold the value that's read back from the switches. In fact, it's going to have just the least significant 4 bits of it will be masked off, so the other bits are forced to 0 through this AND operation. Okay, so, and you'll notice that says here register 5 is affected and register 3 is affected, but it's actually used for the return value. Okay, so what are the implications of using these registers within the subroutine? Okay, so clearly we need registers because many of our instructions, well, all of our instructions rely on registers either for input operands or for the destination for our output. Okay, so registers can be used to also pass values into a subroutine. So before we call the subroutine, we could put a value or a variable into a register, and knowing what register that subroutine expects it to be in. And of course, the registers can be used to return values from our subroutine, like we saw in the example. But if we're going to use registers, we need to be careful to document that, because we want to make sure that any registers that get used or modified aren't holding values that we need in our main subroutine or in our main program. Okay, so we have to be sure to document what's being using to prevent what registers are being used to prevent corruption of data. Okay, so again, just to go up here and think about this particular subroutine, if when if before the subroutine was called, I had some instruction here that used register 5 and was and that value was needed again down later in the main program, this is going to be a problem for me when I call this subroutine, because I'm going to use register 5 in the subroutine as well to hold the address of the input port switches, or the input port that the switches are attached to. Okay, so now if I go back to use register 5, expecting this value that was put in there previously, well, it's not going to have that value. It's going to have some value that is put in there by the subroutine, in this case the switches. Okay, so we have to be careful to document, like is being done right here, so that I know, okay, if I'm going to use this subroutine, I have to make sure that I don't have anything stored in register 5 that I'm going to need to be retained through that subroutine, and register 3, because register 3 is going to have a value written to it that is coming from the subroutine as a return value. Okay, so for this reason, we have to be careful to properly document our subroutines. So documentation, and this is just can be just in the form of comments, should include the following. Should include the name of the subroutine, should include name of the programmer and date of last modification, because if your subroutines are well written, they may not just be developed by you or used by you, they may be used by others as well in your team. And you want to be given credit for your subroutine, or maybe blame if it doesn't work as expected. We want a brief description of what the subroutine does. Again, this may be for others that are using your subroutines. Maybe you've built up a whole library of subroutines that people in your team are drawing from. We need to have a description so it's clear what it's doing. May even be helpful for yourself. You come back to your code later on. It's important that you it'll be important that you have those descriptions to jog your memory. Okay. Also want a detailed description of any noteworthy behavior, whatever that may be. We want to details of what input values, if any, there might not be any input values necessarily, but what input values are passed to the subroutine. Oops. And how. In the case of assembly language, the how is going to be what register. And of course, we also need to know what return values, if any. Oops. What return values, if any, are passed from the subroutine. And again, and how, and the how in our assembly language is going to be what register again. Okay, and finally, what registers are affected. Okay, super important to make sure, again, that we aren't having registers, the data in registers unexpectedly corrupted because we didn't make it clear that registers were being used in the subroutine. So let's just go back up and look at our example subroutine and see if we've done a good job of providing all these details. So name of the subroutine, we haven't really explicitly given it a name here. Name of the programmer and date of last modification, that's missing here. Brief description of what the subroutine does, so that is provided here, so that's good. Oops. Provided here. Detailed description of any noteworthy behavior. We don't really have any noteworthy behavior that's not described just from the description. What inputs are passed to the subroutine? So we don't have any inputs per se. It might be good to note that you expect and equate the switch's value to be equated to the input port address. What return values are passed. So we say here that return values is passed through R3, and what registers are affected. We also mentioned R5 here. Okay, so we've got most of that covered in our example, but again, you should make sure to give your subroutine a name, and maybe it's just in this case maybe it's just read SW. That's fine, and make sure you put your name if you've written it and when it was last modified, so you'll know the modification dates for you. You can be aware, am I using the most current copy of this subroutine in my program? Maybe you've updated it since. Okay, so the this idea of the registers being affected is seems like it could be problematic, particularly if you have a subroutine that's using a lot of registers. So ideally, our subroutine would only modify registers required for return values. Right? We need registers for return values, but it would be nice if we didn't modify any other registers other than that. Okay, so how is that possible? Well, this leads us to talk about the stack. Okay, so this is where the stack comes in. Okay, so what is the stack? The stack is a special section of memory set aside as temporary storage. Okay. We'll look at examples here in a second as well. And as such, it's available for temporary register storage. Okay, so this seems promising to tackle the idea of having none of our registers affected when using a subroutine. Maybe we can store them temporarily and then restore them when the subroutine is done. Okay, so how is this done? Well, in assembly language, or specifically in assembly language for our NIOS 2, we can use a .skip directive. I think we talked about this previously, but if not, the .skip is used to allocate it actually skips a certain number of bytes as specified in the .skips command, but in our case we're using to allocate a section of memory to be used for our stack. Okay, then we'll use a label to hold the address of the end of our stack, and that label for our development environment needs to be called stack top. And it identifies the end of the memory location allocated for stack. Okay, and then finally we use the stack pointer SP to keep track of where we are in this stack memory. Okay, and it points to, or contains, the address of, in other words, the last value sent to the stack. Okay. So we have to initialize that stack pointer when we before we start making use of the stack, and we do that by taking the address of stack top and storing it in the stack pointer register. Okay, so we'll look at an example that lays out the memory here, and maybe this will be a little bit more clear, and as we talk about how it's used. So now the stack pointer, in fact, initially has the address of the location just past the just one byte past, or one address past the last location available in the stack. Okay, because that's where stack top, right? Stack top identifies the end of the memory location allocated for the stack. Okay, so here this command is used to initialize our stack. Okay, how do we make use of this space to store registers? Well, generally, when you talk about using the stack, we use push and pop operations to put values on the stack and to take values back off the stack. So the push operation is used to store a value contained in a register on the stack. In a register onto the stack, so into that temporary memory space that we've allocated. Now, unfortunately, the push operation is not implemented in the NIOS 2 instruction set. So we have to create a push instruction on our own, and we will um, often define it using a macro, which we'll look at here in a second, so that we can in fact use the push instruction within our code to make it a little bit more clear. But we can implement it more explicitly with the instructions that are available as follows. So keeping in mind that we start with our stack pointer pointing just beyond the memory available in the stack, or the last memory location in the stack, then the first thing we have to do is actually adjust the stack pointer to the next available space in the stack. So we subtract 4 off the stack pointer, and then we can use a store word to take a register, in this case register 5, and put it at the location specified by the stack pointer. Okay, so both of these lines are the equivalent of a push of register R5. Okay, so that just took the value that was in register 5 and stored it temporarily in this memory, the stack space that we've allocated. So now thinking about my subroutine that's up above here, our example subroutine, now if I call this subroutine, I don't have to worry about the fact that R5 is affected because I've stored a copy of whatever was in R5 with push. I call my subroutine, R5 gets used to store the address of the switches port, but when I'm done I want to restore the value that was in the register R5, so I use a pop instruction, or in this case operation, since the instruction doesn't exist. Okay, so pop operation is used to retrieve a value from the stack. And place that value into a register. Okay, again, unfortunately pop is not implemented in the NIAS2 instruction set, so we have to create the instruction as follows. Okay, so the pop instruction, we take and load the word that's at the memory location referred to by the stack pointer, and we specify where we want that word to be loaded to. Right, we want to put it back into register 5, and then we adjust our stack pointer to free up that memory location in the stack by taking the stack pointer and adding 4 to it. Okay, both of these lines are the equivalent of a pop of R5. Okay, let's look a little bit more detail of what this stack looks like and how we initialize it. So here's an example of using a block of memory that starts at address 100. Notice we use the .org command to put ourselves at a specific address. So maybe we want to put this at an address that's away from our other code. Whatever is decided is fine. Here we've said we're going to skip 200. Remember, dot skip is in bytes, so we are reserving 200 bytes for our stack, but we'll remember that that only allocates 50 words, because each of our words, each of our registers is 4 bytes in size. Okay, so basically, just let me just kind of show what we've done here as we go. So .org placed us at this location in memory, which is 0x100. We've then skipped 200 bytes, so we set aside this much memory, and then I've used an address label to label, and that actually refers to the byte just, or the address just beyond the end of the stack. Okay, so it's actually the next address because this came after the .skip command. Okay, and then when we start, we say I'm going to set my stack pointer equal to stack top. So that's just initially. So my stack pointer is equal to this to start. So then when we actually go and make use of the stack, and scroll up here a little bit if I can show these, right? It's when I want to put a value in the stack. Okay, so I'm increasing, you know, if this is address, if this is address 0x0100, then this is address, this last address is 01C8, and the stack top is one location beyond that, C9. Right? This is the stack top address. Okay, so when we go to push a value in there as shown here, the first thing we do is we adjust our stack pointer and add 4 to it. So we move our stack pointer up to point up 4 locations above 4 locations from the top. Okay, so I'm going to kind of exaggerate the size of this, but let's assume that this is showing a byte wide. Oops. Let me clean this up here a little bit. We assume that we've just moved up here by 4 bytes. So now the stack pointer is pointing here, and now with my store word command, I'm going to put R5 into this space. Okay. When I'm, maybe now I call my subroutine or whatever it is that I had to do, and then I'm ready to take the value back out of the stack. Well, first thing I do, stack pointer still pointing at the location where register 5 is stored, right here. So first thing I do is load the word that's at this location specified by the stack pointer back into register 5, and then I adjust my stack pointer to free up that space again. So my stack pointer will move back down to be, in this case, equal to the top of the stack. Okay. It's important, so we can of course store multiple registers in the stack. We can push multiple times and then pop multiple times, but we have to be aware of the structure of the stack in that the first value that we retrieve from the stack using a pop is the last value stored by a push. Okay, this type of register or buffer is called a last in, first out buffer or memory. Last in, first out, or LIFO. Okay, because again, if think about this for a second, if I do a push to the stack, I'm just going to clean this up here for a second. If I do a push to the stack, say I put R5 in here, it takes up 4 addresses, and my stack pointer points at the first address of those 4 bytes. And then maybe I do a push of another register. Maybe I push in register R7. Now my stack pointer is pointing to the first byte of R7. Maybe I'll do another push and push in register R10, and my stack pointer will be pointing at R10. So when I do my pop, the first pop I do is going to use the location of the stack pointer, and it's going to give me register R10, the last register that was pushed into the stack. Okay, so we can now appreciate that the stack may be used to ensure registers are not affected by a subroutine. This is how we started this discussion, saying what we really want is to have our subroutine not affect any registers other than the register used for the return value. Okay, so through the use of a push, we can put a register to the stack before our subroutine. In fact, it'll be the first thing that happens within the subroutine, and then the last thing before the return in the subroutine we do a pop, and this puts the value back into the register after subroutine. And again, after, in fact, you'll do it right within the subroutine immediately before the return instruction. So everything is contained within the subroutine. So from the main program's perspective, all of that work to preserve the registers is done transparently. Okay, as I said here, it's possible to push and pop multiple registers. But we have to be very careful of the order, right? Remembering that we're going to get the last one that was pushed in is going to be the first one that's popped out. So we pop in the reverse order as what we pushed. The stack, you may not have considered this, but the stack may also be used to store the return address register. So we talked about the return address register being used to store the return address when a call to a subroutine is done. Well, what if we had nested calls? What if a subroutine called another subroutine without preserving the original return address? When we do this call to a subroutine within a subroutine, we've just corrupted the return address or overwritten the return address to get back to our main program. Or maybe for a recursive subroutines where we have subroutines calling themselves, right? To make sure that we have the ability to return back to our main program, we may find it necessary to use the stack to protect the return address register there as well. Okay, some further details on defining push and pop macros that you'll probably find useful as you start using the stack. Here's all you need for code. It's in the course notes as well, to define a macro for push and define a macro for pop. And the RA in this macro will just be replaced with whatever register value you use when making use of the what will seem like a push instruction and pop instruction after you've defined these macros. So macros, you may say, well, what's different between a macro and a subroutine? A macro is not called, it is not returned from, it's just a compiler directive such that when the an assembler directive such that when the assembler sees the push instruction in the code, it will just go and replace that push instruction with these instructions in every spot that it occurs. Okay, so much different than how a subroutine works, where a subroutine is called and uses that same code and that same address of that subroutine every time, whereas if you use a push 10 times within your code, the assembler will insert these instructions 10 times in the machine code that's generated. So just looking at subroutines again with the use of the stack. So here's a subroutine just pulled from the course notes that uses register 5. And again, if we think about the use of that subroutine in a being called from some piece of code, maybe let me move this down, and let's say we had this main program that's calling this subroutine, and if we we're not careful, and in this example we weren't careful to make sure that we weren't using register 5, right? So this is a loop where register 5 is contains the number of times that we want to go through this loop, in this case 10, and it gets decremented each time through the loop. But when we call the subroutine, this subroutine, it says affects register 5. Maybe we didn't pay attention to that, and register 5 got loaded with an IO address, and therefore corrupted the loop counter that was intended to be in register 5 in this application. Okay, so in this case, the loop, the while loop, would never end. It would we'd be stuck in an infinite loop. Now, if we took and replaced our subroutine with one that uses our stack and therefore no longer affects register 5, the problem goes away. So here, the first thing we do in the subroutine is push our 5 to the stack. Our subroutine otherwise looks the same, and then right before the return instruction we pop R5 back, so we return without R5 being affected. Okay, if we just to reiterate the importance of order of pushing and popping when we have multiple registers that we are placing on the stack. Here's an example where we wanted to push R5 and R22 on the stack. That's fine, but we just want to make sure that when we go and pop R5, R22 and R5 back, that we pop them in the reverse order here, right? So remember, this is a last in first out, so the last register that was pushed in onto the stack was R22, so that's going to be the first one we get out, so we have to pop it first. Otherwise we're going to get the data that's restored to our registers will still be corrupted. We could swap the data. Okay, so we've couple things. You'll note that we started using the macros here. Using the push and pop instructions, which I said don't exist within the assembly instructions for the NIOS 2, but I'm assuming that I've defined these macros up above here. Okay, in which case now I can use the push and pop instructions directly. Makes for a little bit more readable code as well. Okay, so we've accomplished what we set out to do. We now have introduced the idea of subroutines to make for more easily maintainable code, code that uses less memory, and code that potentially is reusable in other programs if you are strategic about the development of your subroutines. And further to that, we've made sure that our subroutines, through the use of the stack, have the don't corrupt or don't affect registers that are used other than those registers that might be necessary for return values. There are more examples and a little bit more detail in the course notes in sections 9.1 and 9.2 if you want to look for some further examples of subroutines and the use of the stack.